example question which you can solve. So we have an inclined plane like this, and an inclination of 37 degrees with respect to horizontal. Now in this there's a combination of two blocks. And the blocks are connected by a thread. So this is a rough surface. A and B are connected with a light thread. Mass of A is given to us as 4 kilograms. Mass of B is given to us as 6 kilograms. Okay. If A and B are released simultaneously, from rest with the thread taut, that means the thread is initially in a stretched or tight position, find their accelerations and the tension in the thread. Given that they have coefficient of friction, in the first case, you take coefficient of friction for E to be 0.2 and coefficient of friction for B to be 0.4. In the second case, reverse that. Take the coefficient of friction for A to be 0.4 and coefficient of friction for B to be 0.2. Okay. Same inclined plane, but the coefficient of friction can be different because the blocks are made of different material. Can take obviously G to be 10 meters per second square. So just start with this question, and in the meantime you can send me any other questions and doubts that you have. Okay, Rahil, I have received your this thing, doubts. Okay, and Varun, yours also. So Varun, can you just share the doubts which you have in the DPT? I will discuss with you. So start with this question, and in this obviously you have to start with the free body diagram. Yeah. Okay. So Meenakshi, you sent the answer as the acceleration of block A or block B in the first part, or is it common acceleration? Okay, so that is the first thing that you have to understand in this question, all of you. That okay, good. Yeah. So in the first part, they will have common acceleration. That is correct. So, so as I was saying, that's the first thing you have to understand, that will the blocks move with common acceleration, or will it be that B moves faster than A? है ना? यहाँ पे there are two cases possible. One is that either they will move in such a way that they have common acceleration, but that will happen only in the case where A is pulling B, so that the string is tight. So if tension in the string is non-zero, that means A pulls B through the string, then acceleration of A will be equal to acceleration of B, equal to some common E. Okay. On the other hand, it can also happen like this, that the string becomes loose after a while, because acceleration of A and acceleration of B is not the same. Acceleration of B becomes greater than acceleration of A. So the string, if acceleration of B is greater than acceleration of A, this will imply that the string becomes slack. So tension is zero in the string, and acceleration of A is not equal to acceleration of B. Okay. So when will the first case happen? When will the second case happen? Okay. So for that you have to understand that an independent block with coefficient of friction mu and angle of inclination theta, what is its acceleration? Its acceleration is independent of mass. Its acceleration is g into sine theta minus mu cos theta. So the acceleration depends on mu. Theta is common for both of them. So therefore, this is a case of an independent block as an acceleration like this. So therefore, if coefficient of friction for A is less than coefficient of friction of B, then A will tend to accelerate faster. So that means it will pull on the string. Okay. So that means what will happen is tension will become non-zero and acceleration of A will be equal to acceleration of B. But on the other hand, if coefficient of friction of A is greater than coefficient of friction of B, okay, then B tends to move faster than A. So in that case, the string will slacken, and as the string slackens, tension will be zero, and acceleration of B will be greater than acceleration of A. So that is how you have to understand how this question. Okay. So now based on this analysis, okay, I have told you when case 1 will happen and case 2 will happen. Now you work out the questions. So hope you understood how to deal with each of the cases. Anybody else got the answer? So see, in case 1, what is happening is that mu A is 0.2 and mu B is 0.4. Okay. So let's start with that. So this is that case where A pulls on the string. Because mu A is less than mu B. So tension is not equal to 0 and acceleration of A will be equal to acceleration of B, equal to A suppose. So they will have common magnitude of acceleration. The string will have some tension. So if you look at the individual free body diagrams, for A, the forces will be like this: mg sine theta, cos theta, normal reaction, tension, and friction. So that is mu A N1, okay, and an acceleration of A. So for A, we will have the equation okay, and now mass of A was given to us as it was 4 kg and 6 kg, wasn't it? Yeah, 4 and 6. So this will become 24 minus T minus 0.2 into 32 is equal to 4E. So this equation becomes 24 minus 6.4. So that is how much now? 17.6 minus T is equal to 4A. That's our equation 1 that we are getting from here. Now similarly for block B, the free body diagram will be like this: mg sine theta, tension, mg cos theta, normal reaction, and friction, like this. Okay. So for B we have the equation T plus m2g sine theta minus friction is equal to mass into acceleration. So this will become So T plus 36 mg sin theta will become 60 into 3 by 5. So 60 into 0.6, so that's 36, minus coefficient of friction here is 0.4 for P, multiplied by normal reaction, which is 48, is equal to mx. So that's 60. So this will become 36 minus 48 into zero point 0.4. So that is how much now? 30, 19.8 now. No, sorry, 0.2. Okay, so that will become 16.8. Six. So this is our second question, second equation. Now solve these equations and we will find the acceleration. So equation 1 plus equation 2 will give us so the common acceleration will come out to be 3.44 meters per second square. Okay, so I'll just leave you to analyze this part once and then start on the second part. So in the second part, the rest of the data is the same, only coefficient of friction is reversed. Mu is 0.4 and mu for B is 0.2. Rest of the things are all the same. Okay, so this is part 1. Now part 2 is much simpler, because in part 2 you can see that mu a being 0.4 and mu b being 0.2, so b accelerates faster than a. So the tension in the string becomes 0. So you can just now use the formula. Acceleration of a will become g into sine theta minus mu a cos theta. So that will be 10 into 3 by 5 minus 0.4 into 4 by 5. And acceleration of b will be g sine theta minus mu b cos theta. So this should be fairly easy, because it's direct formula based now. So these are the values you should be getting in the second part. Okay, next I will move on to angle is 37 beta. Angle of inclination is 37 given in the question. Okay, next I'm moving on to some of your doubts from HC Verma. So I will start with question number 10. Then 23, 27 and 31. Okay, so we'll discuss these doubts. So 10th question, it is telling that the angle made by the resultant contact force and the normal reaction exerted by a body on the other is called the angle of friction. Show that if lambda be the angle of friction and mu is the coefficient of friction, then okay, so let's understand this. So basically what it's saying that if on a given body placed on another body or on another surface, Suppose two types of contact forces are acting. Normal reaction and friction. So when we make the free body diagram, see on this particle, we treat the body like a particle. The two contact forces acting are normal reaction and friction. Now it's not necessary that normal reaction is equal to mg, because there could be other forces acting also. We don't know. Okay. So there could be number of other forces acting. So it doesn't really matter. We don't know how much this is. Okay. Similarly, it's not necessary that friction is equal to mu n, because it could be that there is static friction and the block is at rest. So friction could be less than mu n also. Okay. But yeah, one thing we can see is that the resultant of these two forces, which is the net contact force, that is going to be this one now. So if you follow the language of the question carefully, it will tell you that the resultant of the two forces, if that is making some angle with the normal reaction, that angle is called angle of friction, and that is given the symbol lambda. So R here is the resultant of normal reaction N and friction F. Okay. So it is basically the net contact force, because there are two types of contact forces, friction and normal reaction. Now since obviously normal reaction and friction are perpendicular to each other, so magnitude of R will be this. Okay, because always normal reaction is perpendicular as a vector compared to friction. Okay, so you can see from that triangle that tan lambda is equal to F by N. That is the other thing you can see. So these are the two things: the magnitude of the reaction force and the angle it makes with respect to the normal reaction. Now you bring in the inequality concept, that friction is less than equal to mu n. Therefore, R is less than equal to n square plus mu. Now, obviously, can be zero also. So this thing I'm writing has not been asked in the question, but this is the range of values of the reaction force. What has been asked is about tan theta, which you'll get from this. So you can see that tan lambda is less than equal to mu, greater than equal to z. So that is the same thing as saying that lambda is less than equal to tan inverse of mu. So the maximum thing that we can get is tan inverse mu. Okay, so this was the 10th question. You have to just understand the language of the question. Rest it's easy. Okay, next, somebody asked me the 11th question, Sarvesh. So we'll discuss that also. 11th question is comparatively easy. You have to just understand the friction in the free body diagram. So in the 11th question, you have a system of 3 blocks. Two of the 3 blocks are placed on a rough tabletop like this. The third one is connected by the thread, but going around a pulley. So the pulley is clamped to the table like this. And there is this, the block connected here. So this block is a mass of 1 kg, same as this block. So these are A and B. Whereas the third block C has a mass of M prime, let's say, and that is equal to 0.5 kg. Okay. And coefficient of friction for A is equal to coefficient of friction for B is equal to 0.2. So what will happen here is that the string will develop tension. So this tension is, let's say, T1. Assuming the block will move. Okay, our assumption of course may be wrong. The blocks may not move, but we'll have to check that out. Tension T2. So if they are moving, they will have common magnitude of acceleration. Okay. So now just to make the complete free body diagrams. So for A, there will be tension T2 from this side. So friction, normal reaction, weight, and acceleration E. So T2 minus friction is mass into acceleration. Normal reaction is equal to mg. Friction is equal to mu na. So this equation becomes T2 minus mu mg is equal to ma. Now similarly for the block B, there will be a combination of two tensions. T1 from this side, T2 from this side. Friction, normal reaction, weight. They have the same magnitude of acceleration. So when you write this series of equations, the final equation you will get is that T1 minus T2 minus mu mg is equal to ma. You can complete the steps yourself. And the third block C has tension T1. Okay. So that will have the equation that m prime g minus T1 is equal to m prime e. Third equation. Now what you do is just add the three equations. 1 plus 2 plus 3. So plus T2 minus T2 plus T1 minus T1 will cancel out. On the left hand side we will have m prime g minus 2 mu mg. On the right hand side we'll have 2m plus m prime into a. Then you substitute the values. So m prime was 0.5 minus 2 times mu, which is 0.2 into m, which is 1. So let's see if we get A as a positive quantity or not. If we don't, then that means the acceleration is not happening. To g divided by 2m, that is 2 plus 0.5. So let's see what the numerator is giving us. zero point 0.5 minus zero point 0.4, so 0.1 upon 2.5 g. So that is g by 25. Now generally in HC Verma you have to take the value of g as 9.8 instead of 10. So in case you're not getting the numerical answer because of that, just make sure. But I think in this they have taken it as 10 only because the answer is given as zero point 0.4. And then you can substitute A back in the equations to get T1 and T2. So substitute this A in equation 1. From equation 1, T2 will become M into A plus mu G. 2 will become this. And from equation 3, T1 will become M prime into G minus A. So 0.5 into 10 minus 0.4. 4.8 and 4.4 newtons respectively. These should be the tensions. Oh, sorry, mu is zero point 0.2 now. So I made a mistake here. So this should be 2.4 newtons. Okay, so hope this question is clear. Next, we will move on to question number 23. Okay, 18 also. Okay. Okay, so let's work out question 18 first. So 18 is very similar to the question we did today, but only instead of the blocks being connected by a thread, they are placed against each other. And also the angle of inclination is in 18 question 30 degrees. So if coefficient of friction for A is greater than coefficient of friction for B, then B tends to move, it tends to accelerate faster. So therefore, B will push A, and acceleration of A will be equal to acceleration of B. And normal reaction will be non-zero, where N is the contact force between A and B. So that is this possibility. But on the other hand, if coefficient of friction for A is less than coefficient of friction for B, then A just accelerates faster. So they lose contact. In that case, acceleration of A is greater than acceleration of B, and the blocks lose contact as they move. So that is the concept you have to apply here. So in the first case, mu1, which is actually the coefficient of friction for B, is given to us as 0.2, and mu2, which is the coefficient of friction for the 4 kg block, so that's mu A, is 0.3. So you can see that in this case, they have common acceleration E, and the normal force between them is non-zero. Okay, so E is free body diagram. There will be some force with which B is pushing, plus there will be friction. Okay. And B is free body diagram. this normal reaction will be like this. Friction will be like this, and B also has the same acceleration E. So for E, the equation will become mg sin theta plus n minus the mass of A is 4 kg. So 40 into half plus some unknown n minus coefficient of friction 0.3 into 40 into root 3 by 2 is equal to 4e. That's equation 1. For B, we'll have the equation like this. So 20 into half minus n minus 0.4, sorry, 0.2 2. That's your equation. So just add these two equations. So you will get 20 plus 10. Sum of these two, n will cancel out. Minus ये कितना हो जाएगा? 40 into 0.3, so that's 12 by 2. So 6 root 3, और ये कितना हो जाएगा? Root 3. So 7 root 3 is equal to 6a. So solve for a from this. You get the answer. Okay. Well, the second case is much easier. In the second case, what is happening is coefficient of friction for B is 0.3. Coefficient of friction for A is 0.2. So acceleration of A will be greater than acceleration of B. The contact force between them will be 0, and they will just be given by these formulae. Okay. So that's the 18th question. Finish writing this down. Next we'll do 21st. This one, no? This should be 2 root 3. Yeah, Varun, that's correct. So please note that correction in the equation solving. Okay, so you can complete the solving part and check the answer and all later. Let's move on to question 21 next. So question 21 has this situation. We have a rough horizontal floor. Yeah, in the equation we're always using magnitude of the vector load. This is right from Newton's laws onwards, not only in this chapter, but friction and Newton's laws. Now there's a platform kind of thing here, and there's a person standing on the platform. The person is pulling on a thread going around a combination of pulleys. So that now the wall is not necessary also. Now this surface is rough. So the person's mass is capital M, the platform's mass is small m, and this has a coefficient of friction mu. So find the maximum force that the man can apply on the rope. So the man is applying a force F on the rope. That becomes equal to the tension in the rope. So F max such that the board does not slip. This you have to find. Okay. Now F will become equal to the tension in the thread. So make the man's free body diagram. On the man there is tension T upwards, his weight downwards, and some normal reaction N1. And obviously the man is at rest. So first equation. Okay. And for the board, the forces acting are this normal reaction pushing it down, its own weight small mg, okay, some normal reaction from the ground N2, and tension is pulling it from this direction, but because the board is not slipping, so there is static friction from here. The board is also at rest. So N2 is equal to N1 plus small mg. That's our next equation. And T is balanced by static friction. That's our third equation. And the limiting condition on friction is that static friction cannot exceed mu N2. Okay. So between equation 1 and 2, what we can see is that solving this and this together, we can see that N2 is equal to N1, which is capital Mg minus T plus small mg. Okay. So we will substitute this over here. Okay. And the required friction is this, so we will substitute this over here. So T should be less than equal to mu into N2, which is this. Okay. So in other words, 1 plus mu into T, just bring this side, is less than equal to m plus m into mu g. So that means P should be less than equal to, so now remember T is equal to F. The amount of tension in the thread is nothing but the force that the person is applying. So substitute that here. So the amount of force we are applying should be less than equal to, so the equality gives you the maximum force. So this is 21st question. Okay, so note this down properly, and next we will do question 23. So the whole question is just about free body diagrams. Okay, so whatever force the person applies on the thread downwards, that is equal to the tension in the thread. Rest you just follow the free body diagrams. Okay, the person's free body diagram has vertical forces only, normal reaction, tension, and weight. Whereas the platform's free body diagram has vertical forces, along with that horizontal force, tension trying to pull the block, friction trying to keep it at rest. So condition for equilibrium is static friction is balancing tension. Okay, so people, let's come to question 23 next. Hope this one is clear. So 23 is slightly trickier version of the two block problem we had done earlier because it has a third block, but the method of solving it is more or less the same as we had done for the two block problem. So let's look at it in detail. So this is one of the important questions. Though in honestly in neat pattern, this question is not so relevant because not because the question is too difficult for you to solve. You can solve it, but in a neat exam, the number of questions is such that this question is too lengthy. It's not possible to solve it in a minute and a half or something. It's, time frame wise, it doesn't fit into the pattern. But anyhow, you should know how to solve this because your understanding of friction is not complete without this. So this surface is smooth, and here we have coefficient of friction mu1. Here we have coefficient of friction mu2. So given that mass of the block A is 2 kgs, mass of the block B is 3 kgs, and the mass of the block C is 7 kg. Mu1 is 0.2 and mu2 is 0.3. So we'll do one of these parts here. So let's do the more tricky one. So we are applying 10 newtons force horizontally. Let's do the second part on the block B. We want to find the accelerations. Okay. So the same method that I'm using for the second part, you will use for the first and uh, third part also, where you are applying the force on A instead of B or on C instead of B. Like this. So to begin with, we have to understand that the moment you apply force on the middle block, so I'll just show the blocks a bit separated now, so that it's easy to show the friction between them. So the thing is that the moment we apply horizontal force, let's say like this on B, B has a tendency to slip forward. So the friction on it applied by A is backwards, and the friction on it applied by C is also backwards. Whereas the friction acting on A will be forwards, the friction acting on C will be forwards. So the thing is, friction acts such that it opposes slipping. So the block B tends to slip forward with respect to E and with respect to B. So hence F1 is backwards on it. F2 is backwards on it, like this. Okay. And if it's backwards on B, then it will be forwards on A because this is an action reaction pair. So this is the thing you have to understand. Now you have to also see that what are the vertical forces. Then on B, there will be N1 acting from top its own weight and N2 acting from below. Now on C there will be N2, C's own weight and some N3. So you'll also see that N1 is equal to weight of E. So that is equal to 20. N2 is equal to N1 plus weight of E. Okay. So from this you'll understand that F1 is less than equal to mu1 N1. That means F1 should be less than equal to mu1 was given to us as zero point 0.2, so 4 newtons. From this you'll understand that F2 is less than equal to mu2 N2. So F2 is less than equal to, now coefficient of friction is zero point 0.3. So zero point 0.3 into 50 will give us 15. Okay, so this is the other important information. Okay, now with these two informations in mind, what we'll do is for F equal to 10 newtons on B as shown, suppose we assume, if we assume there is no slipping between A and B. So acceleration of A is equal to acceleration of B and F1 is a static friction. So F1 is less than equal to mu1 N1 and also no slipping between B and C. We always start with the assumption that what if there's no slipping? So their acceleration is also common and F2 is also static friction. So F2 will be less than equal to mu1. So what if we start with this assumption? So if we assume this, so what we'll do is that acceleration of A is equal to acceleration of B is equal to acceleration of C equal to A, suppose. So first we make a combined free body diagram of A plus B plus C. So the advantage in the combined free body diagram is that the friction doesn't come in because the friction is cancelling in action reaction pairs. So only this horizontal force, no friction on the ground, is giving the common acceleration E. So the combined free body diagram, this will give you that F is equal to that common acceleration should become 10 by 12 or 5 by 6 meters per second square. Okay. Now we have to check on frictions F1 and F2 to verify our assumption of no slipping condition. This I have to check. Okay. So for to check that, you go back to the free body diagram of block A. Block A पे क्या है? There is only one force horizontally, friction, and it's supposed to have this acceleration. So F1 should be equal to mass of A into this acceleration. So F1 should be equal to mass of A was 2 kg and this acceleration is 5 by 6. So the friction that we require is 5 by 3 or 1.67 newtons. Now remember that friction was like this. So this was less than equal to, I think the value was 4 newtons that we had calculated. Yes, 4 newtons. Okay, so that means we are safe. We have enough friction available. Okay. So this condition, okay. So therefore A and B will move together. Okay. Now similarly, let's check for the second friction. So for that, we'll make the more convenient free body diagram of C, because on C there is only friction acting and C should have the same acceleration. So F2 should be equal to mass of C into this common acceleration. So mass of C was 7 kg into the common acceleration was this. So that is 35 by 6. So that is something like this. This friction required is so much. Now F2's limiting value was mu2 and 2. So that was, check, it was 15 newtons. Okay. So this assumption is also correct. Okay. So therefore, assumption that acceleration of B is equal to acceleration of C is also true. So therefore, in this case, what is happening? And F1 and F2 will be respectively 1.67 and 5.83 newtons, and they'll be both static frictions. So this general method that we have used of solving this is the common method that we will use in all the parts. Okay. So the first and third part also you use the same common method of solving. You start with the assumption that there is no slipping. So if there's common acceleration, then find out how much that common acceleration is. Then fit that value of common acceleration in the individual FBDs to find out how much friction is required. If the friction is within the limiting values, which are 4 and 15, then your assumption is correct. If it is not within the limiting value, then you will have to remove your assumption and take the case where they are slipping. So when they are slipping, they will have different accelerations, but the friction will be kinetic friction. Okay, next 27th question. This one is fairly easy, so I'll just give you the free body diagram. So what is happening is that you have some kind of a table resting on a floor. Now on the table we have a block which is moving like this. Okay. So on the table top we have this block which is in motion. So there will be a friction acting on it. The block has a mass m. The kinetic friction acting on the block will be mu mg, where this coefficient of friction is mu. Okay. But if you look at the table now, the table is at rest. How the table is at rest? Because the block will be applying a kinetic friction forwards on the table, but that will get balanced by the static friction acting on the four legs. So each leg has static friction Fs, let's say. So 4 times Fs has to balance this kinetic friction. That is mu mg because the table is at rest. Okay. So that's question 27. It's a simple question. 28 is little complicated. So I will explain the free body diagram. So in question 28, what is happening is we have one block like this, another block against it like this. And we have friction on both the surfaces. So this surface has coefficient of friction mu1. This surface has coefficient of friction mu2. So first of all, see what will happen is that in the ground frame, if this has an acceleration a1, then this has an acceleration a2 like this relative to the block or relative to the wedge. And actually what will be happening is that from this position, as the wedge moves forward, the block will be moving down. So the block's actual acceleration is in this sort of direction. So the block actually has a net acceleration which is horizontal a1 plus vertical a2. So this is actually the net acceleration of the block. But in the frame of the wedge, it will look like the block is coming down with a2. Okay, so that is it. Now the forces, tension, okay, there will be normal contact force between these two. Okay. There will be friction on the wedge there will be friction downwards like this, and friction here. And apart from that, weight and all that is there. So I'll just make the individual free body diagrams from this. So what you do is the blocks FBD you make in the non-inertial frame of the wedge. So this is moving with A1, and that the block is experiencing pseudo force. So that is it. That is pushing it against this surface. So the surface is applying normal reaction like this. That is creating friction. That is mu1 n. Of course, there's tension in the thread, and in this frame, the relative acceleration is this. Okay. So you have this equation. So from this, you have n is equal to ma1 and mg minus t minus mu1 is equal to ma. So you have these two equations. Okay. Whereas what you do is you make the wedges FBD, okay, in ground frame. But for the wedge, you have to be very careful about all the forces acting on it. Okay. Because there is this pulley attached here. So there is tension, tension, and another tension. Okay. Then there is the block here which is applying normal reaction on it like this, friction on it like this. Okay. Then there is the wedge's own weight, capital Mg, some kind of normal reaction from the ground, let's say n prime, and friction F2 like this, and horizontal acceleration A1. So I'll just show all the forces in a particle type FBD. So T, 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 three tensions acting like this, normal reaction, friction, okay, then its own weight, normal reaction the ground is applying, and then another friction like this, F2. So F2 is mu2 n prime, F1 is mu1 n, and it's having a horizontal acceleration E. So the forces acting on it in the horizontal direction are 2t minus n minus F2 is equal to capital Ma1. So this is your equation 3. Whereas vertically what is happening, n prime is balancing the sum of capital Mg plus this friction plus tension. Suppose. Okay. So these equations. So now your variables are n, t, a1, a2, and also n prime. So 5 variables, and you have 4 equations. So one additional equation will come from constraint. So constraint relation क्या होगा? Conserve the thread length, and you will understand that a2 is equal to twice of a1. As you can see in the diagram above, if the block moves through a distance x here, so how much thread gets released from this segment? 2x amount of thread gets released. In the same time, if the block moves down through a distance of y, it pulls that much thread. So the amount of thread pulled by the block should be equal to the amount of thread released when the wedge moves. So y is equal to 2x, where y is the downward displacement of the block and x is the horizontal displacement of the wedge. So from this you will get that a2 is equal to twice of a1. So that is your constraint relation, which is the fifth equation. Okay. So now once you solve these five equations, you will get the required answers. Okay. So again, this is a very lengthy question. So just do it for your understanding of friction. But remember that in NEET you will not get such lengthy questions because the time frame of the exam is not like that. So, okay, so that's it for today's class, people. Make sure you note down these equations here and try out solving them yourself at home. Okay, so with this we complete friction. Next week we'll be starting with the chapter work, power, energy.